Yes, especially I would like to talk about ZIF distribution. ZIF distribution is very ubiquitous in complex system. And second, I will give some example of application of discrete or of continuous distribution in biological systems. This is Professor Zipf. He was extremely interesting person. You know, Benoit Mandelbrot sometimes say that, one time say that he discovered his geometry, fractal geometry, due to interest which rises to him the Zipf distribution. This is one of the enemies. As any genius, Zipf has many critics. This is one of his critics who speak about this, but this is not exactly correct. Mathematically, this is the Zipf distribution. You see this S is a Riemann zeta function. It is sum of this simple series. When S equal 1, we have harmonic series. But when S not equal 1, it is Riemann function. This is harmonic series diverge, yes? And this is the problem for normalization of Zipf distribution. But instead of harmonic series, we can introduce harmonic number. Harmonic number is a generalization in the sense that we substitute infinity in this sum by n, finite number n. And the harmonic number is not divergent, it is finite. And gamma here is an Euler constant. E in potential gamma is this number. This number is important in Zipf distribution. Next. Zipf, there is two laws. The Zipf first law and Zipf second law. The first law speaks about the constancy of the product of probability of words in a text with rank of the word. And Zipf tries to explain this by introducing the idea of the least effort hypothesis. He said that the speaker is using few words. The hearer demands the specific words to understand the speaker. Yes. In a very simple representation, the Zipf distribution can be represented in such a manner. When R is rank and P1 is probability of the most frequent word in the text. Sometimes it is useful to represent Zipf distribution in log-log plot. Many complex systems follow Zipf pattern. Zipf law is very well-known empirical law. From many social and physical sciences, data follow the Zipf law. This is the example of the systems which follow Zipf's law. This frequency of words in English, for example, text, or any language text, or even in any artificial language text. US firm size is Zipf distributed. City sizes in the industrial regions are Zipf distributed. Zipf law governs many features of internet. In programming languages construct also follow the flow. The now very common chat robots also using the flow. It is interesting to note that the book of Zipf, The Human Behavior and the Principle of Least Effort, and the book of Claude Shannon, The Mathematical Theory of Communication, are published in the same year. It is not simply accident, because Shannon used the Zipf flow to calculate the entropy of English text. This formula is Shannon formula obtained by the help of Zipf distribution. For example, here is a example of the Zipf law, empirical facts about from the famous Alice in Wonderland. We see that it follows almost very well to the Zipf distribution. Zipf explanation of this fact. He said that both speaker, this is in some sense a teleological explanation. Teleological. He said that the speaker and hearer trying to minimize their effort in communication. The former's effort is conserved by having small vocabulary of common words with large probability. And the hearer effort is the desire to having large vocabulary of specific words, rarer words, yes, small. So the message can be less ambiguous. The Zipf law represents an optimal compromise between this opposite effort. This explanation is explanation only theoretical, philosophical, but it does not give mathematical passage to the Zipf formula. But Zipf used in his famous book very many teleological and philosophical arguments, and it is funny how rich is this book, this text, his book. The second thought is much simpler. The shorter words are more often than larger words. That shorter words, for example, the, of, and, a, and so on. And larger words have smaller distribution, smaller probability in the text. This he explained it. Zipf explained this phenomenon that biological organisms strive to spend little energy as possible, and Zipf argues that in speaking, they use considerable amount of energy and to speak, and short words need smaller energy. Large words, and this is some principle of economy of the energy, which brings to the Zipf distribution. Now, I finish it with this discrete distribution, and I would like to talk about continuous scaling in complex system. You know, this is the simple power law. Fx equals c multiplied by x in power n. This is simple polynomial, yes? And from dimensional analysis of this line gives that dimension of c is equal to dimension f divided by dimension of the variable x in potential n. Variable x here is continuous. In Zipf distribution, in discrete, it was take integral values 1, 2, 3, but here it is continuous variable. The notion of scaling is that under the transformation, lambda transformation such, the form, the shape of function remains unchanged. It is shape invariant. According to the Euler, we say that this this law, this scaling law, is homogeneous of degree n. If we differentiate this equation, we obtain input lambda equal 1. We obtain a differential equation, integration of which gives this the same polynomial power law. In nature, there is many scaling laws. You can open the site in Google, such scaling site Nobelprize.org, and there is 100 results from the Nobel laureates talks about scaling distribution in physics, biology, and social sciences. Yes. Now I am considering one very particular case example from biology, the scaling of metabolic rate in the organism. It is interesting to understand how metabolic rate changes from mouse to elephant, or in other words, from the mass how depend the metabolic rate from the mass of the organism. How is weight, from the weight of organism. It is interesting that it changed according to some power scaling law. Probably it scales like m, like mass of organism, in potential 2, 3. If mass increases 1,000 times, the energy for sustaining organism increases only by factor 100. This metabolic rate of rest state, when organism is in rest state, without any work, without any spending of energy to other activity. It is apparent that theoretical elucidation of the universality of scaling law in complex physical and social system. This is the last sentence of my talk. Yes. Let's consider the mouse has a very large, has mass to 23 grams, and his metabolic rate is approximately 100 of watt. The metabolic rate, or in other words, the basal metabolic rate, the metabolic rate when the organism is sleeping, not working, is very important quantity in biology. For example, a human with mass 70 kilogram, every second have waste 80 joule, or he has power like one electric lamp. And for example, larger animal, excuse me, we are not animal. Next. He spend nearly 1 watt for 1 kilogram. He generate larger animals generate 1 watt for 1 kilogram. There is some questions. What is the scaling exponent, 2, 3, or 3, 4? Historically, the exponent of metabolic law was proposed by Kleber as a mass in potential 3, 4. But now, today, new data, and there is a very great controversy, and probably the potential not 3, 4, but 2, 3. 2-3 has very simple meaning from dimensional analysis. It is the ratio of area of object to its volume, because the generation of energy, the radiation of energy occurs through surface, but the generation from the volume. And for this reason, probably the scaling law is m in potential 3, 4. Yes. There is some connection with it, metabolic rates of living organisms. It is also a living organism, between animals metabolic rates and plants metabolic rate. The greatest living organism is sequoia, and it is interesting that there is some laws, some scaling laws, which connect the metabolic rate of sequoia with metabolic rate with small plant, with small domestic plant. And this show that the life is universal, has universal properties. Thank you.